Hello. In this lecture, we will discuss the conversion of a hexadecimal number to its octal equivalent. Now, before we actually start with an example, let us quickly recheck the table of hexadecimal, decimal, and binary numbers. Here we have the table of hexadecimal and decimal numbers along with their binary equivalents. So, for example, we have the hexadecimal number 0 with its decimal value equivalent to 0, and in terms of 4-bit we can write it as 0000 as a 4-bit binary, and like this we have it for hexadecimal 1 2 3 up to f. As we know, stands for the decimal number 15, which can be written in terms of 4 bits 1 1 1 1. So for representing the hexadecimal symbol f, we require 4 bits. But when it comes to octal numbers go from 0 to 7. So if we look at the last octal digit here, 7, this requires only 3 bits, and therefore every octal number can be represented in terms of 3 bits. So here is the important point in this table. A hexadecimal number can be represented using 4 bits, whereas an octal number can be represented using 3 bits. Now, with this background, let us start with an example. In the first example, we are given a hexadecimal number CAB. This is in base 16, and we want to convert it into its octal equivalent. So the steps to this are as follows. In step 1, we will first convert the given hexadecimal number to its 4-bit binary equivalent. We saw in this table that every hexadecimal number can be expressed in terms of 4 bits, and this is the logic we apply here. So CAB can be written as C can be replaced with its equivalent binary value 1100. So we can refer to this table here. We have C as 1100. This is the equivalent binary value of C. A can be represented as 1010. Here we have the equivalent value for A. A can be represented as 1010, and B can be represented in 4-bit binary as 1011. Let us verify this part. B can be represented as 1011. So we have the hexadecimal number, and each digit of the hexadecimal number has been expressed in terms of the 4-bit binary equivalent. Now, in step 2, we start from the least significant bit. This is our least significant bit, and from here we form groups of 3 bits as we move from the least significant bit to the most significant bit. So starting from the LSB, let us form the groups of 3 bits. So we have 110 followed by 101. This is as we are moving from the right to the left. Then we have the next 3 bits 101. Sorry, that is 010. So you have 010, and the last 3 bits 011. These become the last 3 bits. So we take groups of 3 bits starting from the least significant bit and keep moving towards the left. Now we start from the least significant bit again in this step 2, and we'll replace each group of 3 bits with its equivalent octal digit. So for example, this group here 1 1 1 1 1 and 0, this will be replaced by its equivalent value in octal. So we have here 6010 can be replaced with its octal value 2, 101 its octal value is 5, and 011 can be replaced with its octal value 3, and therefore the given number CAB is equivalent to 6253 of octal. Let us take the second example where we are again given a hexadecimal number, but this time this number has a fractional part. So we have, before the decimal, we have the integer part 54. After the point, we have the fractional value FB32. Now to convert this, we will write our given decimal number as 54.FB32. Again, as in the previous case, we take each hex digit and express it in terms of its equivalent 4-bit binary. So the 5 can be written as 0101, 4 can be written as 0100, the point is kept as it is, F can be replaced with its binary equivalent 1111, B can be represented with its binary value 1011, 3 is 0011, and this digit 2 can be written as 0010. Again, we form groups of 3 bits starting from the decimal point, starting from the point. Now observe this. We start from the point. As far as the integer part is concerned, we will collect 3 bits at a time. So we'll have 0, 0, 1. This becomes our one group of 3 bits. Then we move forward. We have 0, 1, 0. This becomes our next group of 3 bits. And then observe this. We need 3 bits. So we pick up the bit 0. We pick up the bits 1, 0, and we don't have another bit here, so we pad it with a 0, with a leading 0. So we have the 3 bits 1, 0, 0, reading from right to left. And now each of these groups of 3 bits, we replace them with its octal equivalent. So this becomes 1, 2, 4. We have the point, and now here again we convert each of these bits into groups of 3. So now let us start from the point, and now we move from the point towards the right. So we'll have a group of 111. This is a group of 3 bits. Then we have 110. This group is 110. Then we have the next 3 bits 110. That is 110. The next 3 bits 0, 1, 1, and the last 3 bits 0, 0, 1 is this. This 0 we can discard because it is not significant here, and therefore this each group of 3 bits can be again written in terms of its equivalent octal value. So 111 becomes 7, and similarly we have 110, 6, 6 for this, 011 becomes 3, and 001 becomes 1, and therefore the equivalent value can be written as 124. This is the part that appears before the decimal point, followed by 0.76631. So we have 0.76631. So this becomes the equivalent value in octal number system.